Hello everyone. Welcome to another episode of Deep Dive Knowledge Talk. Hello. I read the summary of your study on DocLLM, and I'm really intrigued by your approach to multimodal document understanding. Could you please explain to me how DocLLM incorporates the spatial layout structure of complex enterprise documents?
Certainly. DocLLM is a lightweight extension to traditional large language models that focuses on incorporating the spatial layout structure of complex enterprise documents. It does this by considering the bounding box information of the text tokens in the document. Imagine you have a puzzle with different pieces, and each piece represents a word in a document. The spatial layout structure is like the arrangement of these puzzle pieces on a table. In DocLLM, instead of looking at the content of each word individually, the model pays attention to the relationship between these words based on their positions on the page. This allows the model to understand the document's layout and how the different words are spatially related to each other. By incorporating the spatial layout information through the bounding box coordinates of the text tokens, which are obtained using optical character recognition, OCR, DocLLM can comprehend the document's structure without relying on complex vision encoders. In summary, DocLLM uses the positions of words on a page, represented by their bounding box information, to understand the spatial layout structure of complex enterprise documents. This enables the model to reason over both the textual semantics and the spatial layout of the document.
That's fascinating. By leveraging the bounding box information of the text tokens, DocLLM can capture the spatial relationships between words in a document without relying on image encoders. This approach seems to be quite efficient and lightweight. Could you please explain how DocLLM extends the attention mechanism of traditional transformers to capture the cross-alignment between the textual and spatial modalities?
DocLLM extends the attention mechanism of traditional transformers by introducing new attention scores that capture the cross-alignment between the textual and spatial modality. This is done in a disentangled manner, treating spatial information as a distinct modality. The attention mechanism in DocLLM calculates attention scores between the text and spatial modalities using projection matrices. These attention scores are then used to compute hidden vectors, which are used as inputs for subsequent layers. To capture the new modality of spatial information, DocLLM encodes the bounding boxes into hidden vectors. These hidden vectors are represented as S in the model. The attention matrix computation in DocLLM is decomposed into 4 different scores: text to text, text to spatial, spatial to text, and spatial to spatial. These scores capture the relationships between the text and spatial modalities. By incorporating these new attention scores, DocLLM is able to effectively capture the cross-alignment between the textual and spatial modalities, enhancing its ability to understand visually rich documents.
Thank you for the explanation. DocLLM's extension of the attention mechanism through disentangled matrices is interesting. It seems that by treating spatial information as a distinct modality, the model can capture the relationships between the text and spatial modalities more effectively. In the study, it is mentioned that DocLLM addresses irregular layouts and heterogeneous content frequently encountered in visual documents. Could you please elaborate on how the model handles these challenges?
DocLLM addresses the challenges posed by irregular layouts and heterogeneous content in visual documents in a few ways. First, it uses a layout-aware generative language model, which means it takes into account both the textual semantics and spatial layout of the document. This allows DocLLM to understand and reason over the visual cues provided by the complex layout of the document. Second, DocLLM incorporates bounding box information, which represents the spatial structure of the document, instead of using expensive image encoders. This means that DocLLM focuses exclusively on the layout information to understand the document, making it more efficient and lightweight. To specifically address irregular layouts, DocLLM employs an infilling pre-training objective. This objective helps the model learn to effectively fill in missing or incomplete information in irregular layouts, allowing it to better understand and interpret documents with non-standard or varying layouts. Moreover, DocLLM utilizes an instruction tuning dataset that is specially curated towards visual document intelligence tasks. This dataset provides specific instructions to the model on how to analyze and understand different types of visual documents, enabling DocLLM to better handle the heterogeneous content frequently encountered in these documents. Overall, by incorporating layout information, using an infilling pre-training objective, and leveraging an instruction tuning dataset, DocLLM is able to handle the challenges posed by irregular layouts and heterogeneous content in visual documents more effectively.
Thank you for the detailed explanation. It's impressive how DocLLM tackles the challenges of irregular layouts and heterogeneous content in visual documents. The combination of the layout-aware generative language model, the use of bounding box information, and the infilling pre-training objective all contribute to the model's ability to comprehend and interpret visually complex documents. In the study, it is mentioned that DocLLM outperforms state-of-the-art language models on various document intelligence tasks. Could you please provide more information about the performance of DocLLM and its generalization capabilities to unseen datasets?
According to the report, DocLLM performs well compared to state-of-the-art language models on various document intelligence tasks. In fact, the modifications introduced by DocLLM result in a performance improvement ranging from 15% to 61% for the Llama 207B model in 4 out of 5 previously unseen datasets. This means that DocLLM is able to generalize well to new and unseen datasets, showcasing its effectiveness in understanding visual documents and extracting key information from them.
That's impressive. It's great to hear that DocLLM not only outperforms state-of-the-art language models on multiple document intelligence tasks, but also demonstrates strong generalization capabilities to previously unseen datasets. This highlights the model's ability to understand and extract valuable information from visual documents across different domains and contexts. Based on the results you mentioned, it seems that DocLLM has significant potential for practical applications in various industries that heavily rely on document processing and understanding. Can you provide some examples of such potential applications where DocLLM could be beneficial? Now,